So I'm sure some of you guys want to talk to me about the project today. You know that the project proposal is due on Wednesday. So I was thinking of cutting the class a little bit short today. So if you can't come to my office hours today, then we can go to my office and talk about the project for a little bit. So that's the plan. And what I want to do today is keep talking to you about small roots. So remember we have this root poset on the positive roots where you have an edge from u to v labeled by si when, from beta to gamma when gamma is equal to si beta, and the depth of gamma is the depth of beta plus 1, right? And then we said that these edges can be short or long. I realize what my confusion is, that roots are small and edges are short. And so whenever I say small or short, I might get it wrong, but it doesn't matter. So roots are always small and edges are short. Okay? So the edge is short if the absolute value of the inner product of beta and alpha I is at most 1. And it's long otherwise. Okay? And I mentioned that you might as well put gamma here because the inner product of beta and alpha I is minus the 1 of gamma and alpha I. Okay? And then I said that the small roots are those reachable from the bottom of the poset through short edges. From the bottom by walking up short edges. Okay. So this was the definition of small root. And we talked about a different characterization of small roots, which was the following. This domination poset. So we said that gamma dominates beta when every group element that makes beta negative also makes gamma negative. Okay. So that's domination, and we talked about this proposition or theorem that small roots are exactly those that don't dominate anybody. And that means that we have these two alternative ways of thinking about small roots. Okay? I realized that when I gave you a sketch of this proof, of the proof of this proposition, but I didn't actually talk about why this 1. And that's one thing that I want to tell you today. Why is it that 1 is some kind of threshold here? And so let me just tell you the key thing about this 1 that we have here. Okay? And it's this lemma. So the key thing about having the inner product of two roots be less than 1 is this lemma. And it says the following. It says, if the inner product of two roots is between 1 and -1, so that's a geometric fact, then that translates into a fact about the group, which is that the subgroup generated by the corresponding two guys is a finite dihedral group. Then the subgroup of W generated by the corresponding group elements, each root corresponds to a reflection. This is a dihedral group, a finite dihedral group. Okay? And so that means that this is some kind of finiteness condition. Now, if the inner product is less than or equal to -1, then that's where the threshold happens. And then all of a sudden, this finite dihedral group becomes infinite. Then this subgroup is infinite. And not only that, but if you look at the different roots that are generated in this way, yeah, I mean, these are all elements of this subgroup, right? T beta, T gamma, T beta, T gamma, T beta, T gamma. And now, if you see what these different elements do to the roots, they really just bounce them into more and more positive roots and different from each other. Okay? So these are distinct and positive combinations of beta and gamma. Okay? So maybe the details of this lemma are not so important, but I want you to think about what this lemma means. This lemma means that really there is a threshold that takes place exactly at 1, okay, where a subgroup goes from being finite to being infinite. And when you look at what that means in this context, it's exactly what you need to characterize small roots. Okay? And so this lemma appears in several different places when you work on this, and that's the reason why we have a less than 1 here and not a less than 2. Now, why? So now the question is, okay, why 1 here? You know, I'm telling you it's a 1 here because it's a 1 here, but why is it not a 2 here? What's the key thing about having a 1 here? And the thing is that it's actually a geometric fact. I mean, we talked about how finite Coxeter groups can live in Euclidean space and infinite ones cannot. And really that's what this is about. Because if you try to fit this situation into Euclidean space, think about it. You have to build two vectors beta and gamma. They're going to span a two-dimensional space, right? And so all you get to choose is the angle between them. Okay? But they have to be unit vectors because they're roots. All you get to choose is the angle between them. And the question then is, what can this number be in Euclidean space? Well, it's between -1 and 1 because it's the cosine of the angle. Now, can it be 1? Well, it could be 1 if beta and gamma are the same vector. But then they wouldn't be linearly independent like they're supposed to be. Okay? So that means that this cannot be 1. It has to be less than 1. And can it be -1? Well, geometrically it could, except that beta would have to be the negative of gamma. Again, they wouldn't be linearly independent. So in Euclidean space, you must have this. If this is Euclidean. Okay. And that really is the reason why why it's a 1 and a negative 1. And like I said, the details are in the book, and you can look up these proofs, but this is really the essence of it. Somehow a finiteness condition which translates to a Euclideanness condition. Okay. So what I want to do today is give you some more properties of small roots. So nice properties of small roots. And I want to tell you two kind of useful propositions and then our main theorem on small roots. So the first nice property is the following proposition. The small roots are an order ideal. So what does this mean? In the root poset. That means that if you are smaller than small, then you are small. Yeah. If you're smaller than a small root in the root poset, then you must also be small. It sounds like it makes sense, but it's not obvious, of course. So if beta less than gamma and in the root poset, and gamma is small, then beta is small. And this is not obvious because this adjective of small, as far as we know, is not necessarily related to smallness in this poset. Now, I think if you try to prove this proposition using our original definition of small roots, it's pretty tricky, but using the work that we have done, this is actually pretty easy. So let me show you the proof. The proof just says, okay, well, suppose we have this gamma, beta, and small. Okay. Now, look at this edge. I mean, I should say, of course, it's enough to prove this for covering relations, right? So if I want to show that yeah, I mean, it's enough to prove this for covering relations, just for the minimal relations in the poset. So let's take a covering relation like this, and where the top element is small. Now, is this a short edge or a long edge? Well, if you remember, we showed last time that if you have a long edge, then the top guy is not small. Yeah. That means that this is a short edge. Yeah. So this is a short edge. And then if you remember, we also proved that smallness is just propagated up and down short edges. Along a short edge, either both of these guys are small or both are not small. So small implies short, implies small. This is when I finally realized why I kept messing up the small and the short. Okay. So that's the proof. Small implies short implies small. Okay, good. Second one. Proposition. If the group is finite, then this might be a bit of a surprise to you. If a group is finite, every root is small. So what that says is that really the notion of smallness is only useful when we're talking about infinite Coxeter groups. But for finite Coxeter groups, it's just a vacuous adjective. Okay. So let's prove this. To prove this, I need a couple of lemmas. So step one, lemma 1. Lemma 1. If beta dominates gamma, I have gamma dominating beta, so let me do it that way. If gamma dominates beta, then the depth of gamma is bigger than the depth of beta. Okay. Again, maybe that sounds reasonable, but this is somehow saying that domination and depth are compatible. Okay. So let's prove this. Let's prove this. Remember what depth means? Depth is the shortest length of an element that makes you negative. And so let's take a shortest element, W, which, I have to be careful because in my notes I had it backwards. So let's consider this. Consider a group element which makes gamma negative and is the smallest possible. Okay. And let me just write it as, I don't know, S. Just let's take some reduced word for W and let this be the first letter. Okay. So basically what I'm saying is that, well, first of all, W prime is shorter, and because it's shorter, that means that it doesn't make gamma negative. Right? So W prime does not make gamma negative, it makes it positive. Okay? But this says that W is SA times W prime gamma, and that is negative. And we like this because we know what is the only positive root that is made negative by a simple reflection. It must be the corresponding simple root, so W prime gamma must be alpha A. It can't be anything else. Okay? Okay, now, what I want to do then is say that beta cannot have the same situation. So, gamma dominates beta, right? So, because gamma dominates beta and W gamma is less than 0, that means W beta is also less than 0. Okay? Now, let's consider W prime beta. And let's ask ourselves, because the point is this. What I'm trying to do is, I have some depth for gamma. I want to show that the depth of beta is smaller. Now, I already found something of length depth gamma that made me negative, but I want to show that I can make this smaller. Okay? And what I'm going to show is that W prime already makes beta negative. So that's my claim. I have that W beta is negative, but I want to show that this shorter element also makes it negative. And the proof of that is that if it was the other way around, then we would also have SAW prime beta negative. But again, we're in this situation where we have a positive root that is made negative, and that's very restrictive. That tells me that W prime beta would be equal to alpha A. But W prime cannot take two different roots into the same root because these things act as permutations on the roots. Okay? So this is a contradiction. Okay. What that means is that I already found something of this length. So the depth of beta is at most the length of this word, the length of this element, but the length of W prime is strictly less than the length of W. And the length of W, by definition, was the depth of gamma. So that's the end of my lemma. And that proves that domination is compatible with depth. Okay. So let's go over there now. Actually, before I say anything else, let me give you a strengthening of this. Let me give you a strengthening of this lemma, because this domination poset we don't understand very well yet. So let me show you a nice way to understand it that I won't use right now, but it's good to know. Proposition: gamma dominates beta if and only if. I mean, the question is how strong is this? So to dominate beta, you must have this condition, and you probably need something else, right? And what you need is exactly that. The angle between beta and gamma is, you can imagine, greater than or equal to 1. Okay. So this is just for your information, in case you ever need to know whether a root dominates another one. This is one way to do it. Okay. So it's what you need to make a converse out of this lemma. Okay. So that's my lemma 1. Now my lemma 2 is going to be the following. Remember, I'm trying to prove that if a Coxeter group is finite, then every root is small. And so how am I going to use finiteness here? Lemma 2 says that let W be finite. So if it's finite, that means that it has a top element, W naught, okay? And I can consider the following, no, not this. I can consider the following map, the map that takes a positive root and sends it to W naught beta. Leave a little space here. I start with a positive root. What does W naught do to a positive root? Well, remember that the number of positive roots that become negative by a group element is exactly the length of the word, of the element. And this element is the longest possible. The length is exactly the number of roots, which means that this element makes every positive root negative. Okay? So this map takes positive roots and sends them to negative roots. But I like positive roots better, so let me just put a minus in front of this, and now it's positive. Okay? So this is a map from positive roots to positive roots. And what you hope is that this behaves under these different notions. And it does behave in a very interesting way, because it is, first of all, depth preserving. Okay? So the depth of the new guy is the same as the depth of the old guy. But the interesting thing about this is that it is domination reversing. Okay? And this should sound strange to you, because I just proved that domination and depth are compatible with each other. And yet I'm telling you that, that this thing does one thing to depth and the opposite thing to domination. Okay? Well, what this is going to prove is that basically there isn't any domination, because precisely because there is this strange map that is doing supposedly one thing, supposedly another thing. Okay. So it preserves depth and it reverses domination. So let me just give you an idea of how to prove these things. Okay. First of all, we already justified why this goes from positive roots to positive roots. Now, why is it a permutation? Well, one way to see that is, you have to invert this. And one way to see that is that actually this is an involution. If you multiply this by W naught and put a negative sign in front of it, then minus times minus is plus, and W naught times W naught is also plus. It's also the identity. Yeah? So this is an involution, which means there must be a permutation. So it's an involution. So it's a permutation. The inverse is itself. Okay? And now I need to prove that it preserves depth and reverses domination. So let me just show you that. So depth. I need to prove that this guy and this guy have the same depth. Okay? The way I do that is I suppose that I take an element of the correct length, and I have to now produce an element of the same length that makes this guy negative. How am I going to do that? Well, you just play around with this a little bit, and you realize that one way of writing this is like this. You need to take a group element times, you need a group element of the same length times this other root to be negative. Okay? But so far, this W naught and this W naught cancel each other, and I put a minus sign and I get something positive. I want something negative. And by the way, I want something of length W, and this does not have length W. So how do I fix that? The way that I fix that is by now acting on this thing by W naught. This is some root, some positive root, and W naught makes every positive root negative. So because this is positive, this is negative. Okay. So now I have some group element that sends my root into a negative root. And the question is, what is the length of this group element? Well, if you remember what multiplication by W naught does, either on the left or on the right, it flips the poset. And so what I'm doing is I'm flipping the poset, and then I'm flipping it over in some other way, but the ranks are reversed and then preserved. So this thing has length equal to the length of W. So I just produced a group element that sends this guy into a negative, and so that means that the depth of my new guy, the depth of minus W naught beta, is at most the length of W, which is the depth of beta. Okay. So I proved one direction, but I need to prove that these things are equal to each other. The nice thing is that because this is an involution, that means that if I apply exactly the same procedure to minus W naught beta instead of to beta, I'm going to get exactly the opposite inequality. So because of the involution, this is also greater than or equal to, and therefore it's equal. Okay. So that proves that this thing preserves depth. Okay. Now let's prove that it reverses domination. So what does it mean to reverse domination? It means that you want to start with a domination relation, and you want to get to the opposite domination relation for the minus W naught times this thing. Okay. So what does it mean for gamma to dominate beta? It means that W gamma less than 0 implies W beta less than 0. What does this mean? This means that if W beta is greater than 0, then W gamma is greater than 0, right? It's the contrapositive. What does this mean? Let me now just, this is true for W, for any W, and in particular it's true for W, W naught. It's true for every group element, so it's true for this guy, and I can do the reverse thing as well. Okay. And now let me just switch the sign of this thing by saying that W of minus W naught beta is negative, implies that W times minus W naught of gamma is negative. Okay. And what I just proved is that minus W naught beta dominates minus W naught. So that proves that this map is domination reversing. Okay. And with this information, it's now very easy to prove my proposition. Proof of this proposition what I'm going to prove is that basically there's no domination in a finite group. Okay? And there's no domination because of this map that does supposedly two opposite things. So suppose there was a domination. In W. Okay? Well, that means that minus W naught beta dominates minus W naught gamma. Okay? Because of domination reversal. Now, domination reversal. Now, if gamma dominates beta, then by my lemma, the depth of gamma is bigger than the depth of beta. And if this dominates this, then the depth of this is bigger than the depth of this. Okay? But this map is depth preserving, and that means that actually this thing is equal to this one, and this thing is equal to this one. And yet I'm saying that it's bigger than this one is bigger than this one, and this one is smaller than this one. But that can't be. By depth preserving. Okay? And so that's a contradiction. That's a contradiction to assuming just the simple fact that there's any domination. And what that means is that if you have a finite root system, a finite Coxeter group, then no root dominates any other root. And therefore, everything is small because no one dominates anybody. So there's no domination relations. So everyone is small. So that proves proposition 2. In finite groups, every root is small. Okay. So if we were to take the analogous statement, you would think that maybe most roots are small in an infinite group, because in a finite group, every root is small. That might be the intuition that you draw from this, but that's actually a very incorrect intuition. And the reason is basically the main theorem on small roots. For a lot of purposes, the most important fact about small roots is that no matter how huge your infinite group is, the small roots are finite in number. The number of small roots is finite.
W can only have finite generators.
Yeah. Finitely generated W, the number of small roots is finite. Why would this not be true for infinitely generated ones? For the obvious reason that simple roots are small. So if you have infinitely generators, then they're all small. Okay. But we talked about how really we care about finitely generated Coxeter groups more than anything. And this should be a very surprising theorem. You have some infinite thing. The root poset is infinite. So I hope you can make sense of when I draw something like this. This really means, we have some simple roots and then other roots, and this thing is, it's humongous. It can be but the point is that the small roots form an order ideal, and it's a finite order ideal, which means that basically small roots are kind of look like this. So there's kind of, you start out by everybody being small, because all the simple roots are small, and then as you go up, what this statement says is that if something is small, then everything below it is also small. So that means there's kind of a boundary here of the things that are maximally small, and that boundary is finite at a finite level, and everything else from the top is infinite. Okay? And this is extremely useful because very often we care about all the roots, but when we want to work with all the roots, we're working with an infinite set. Okay? But the very nice fact about small roots is that there's finitely many of them, and they capture a lot of the structure of all the roots. So there's a lot of things that you can tell about the group by only looking at the small roots. Okay? Which means with finitely many information, with finitely much information, I don't know how to say that. With a finite amount of information, you can tell a lot about the group, which is infinite. Okay? And this main theorem is the main tool that allows us to prove this result that I showed you, that Coxeter groups are automatic. In other words, that you can really program in a very easy way for a computer to figure out if words are reduced or are not reduced. All you have to do is walk around a graph. And that's what we'll prove next time, exactly using this. So let's stop there and let's talk about the projects for a little while. Any questions?
I might be making this up entirely, but was there a time in which you said that W finite implies Euclidean?
Yeah.
And so this proposition here, what kind of light would that shed on that idea? How could we reinterpret that with this new insight?
So that's right. So I talked about how finite Coxeter groups fit in Euclidean space, and they're the only ones that do. Okay. How do you then make sense of this in that light? Well, I guess one way of thinking about this is for finite groups, you have this Euclidean model that you're used to and you can think about. And for infinite groups, what do you have? Well, so far we didn't really have very much to work with. And now we have something that is a tool for making something infinite into something finite. And then we have finite tools to understand an infinite group. We know that a Euclidean picture is not going to work, but this is a reasonable substitute sometimes. That's how I would put it. So I could have office hours here, but I guess it's better if we're in front of my computer so I can give you references and things. So if anybody wants to go, let's just run upstairs. Thomson's equation, that's what it's called, yeah. Thomson's equation, I think that's the name of it.
Alright.
I grabbed the book that Smith had recommended.
Okay. Was it by that same lady? Do you know?
No. It's by Grunbaum, and I've read stuff that he's recommended before. Not that there's exactly any more or less readable. This looks like it's very.
I'm waiting to hear back from Christian. He wants to do Schubert things.
How do you feel about Schubert things?
Well, I got some books.
Some other questions.
And it seems to get to Schubert things, I have to get through Grassmannian things and varietal things.
But that's easy. It always sounds harder than it is.
The way
Okay.
that
I mean, I sort of know what a variety is. I've heard people throw around Grassmannian enough to know that.
Grassmannian is the nicest variety.
Okay.
But there's that one easy way of thinking about it. It's just a set of planes and set of k-dimensional planes in time space. Right?
Okay, what should
So how you can make this variety where every point corresponds to one.
And what
Yeah, I need to kick you guys out so I can run upstairs. Sorry.